Graphics pipeline is something that we're going to discuss throughout the rest of this course, and the important thing is it's programmable. Essentially, a graphics pipeline is allowing us to initially examine the vertices and transform them in space. Then from the individual vertices, which are basically just points in 3D space, in the assembly stage we begin to assemble geometrical shapes such as triangles. Rasterization is the next stage, which basically transforms these geometric shapes into a series of fragments. Basically it rasterizes everything, so everything is the entire surface. The rasterization means that the entire surface of this triangle is rasterized into a little parts, and these parts are called fragments. Basically these are fragments of each face that will be rendered. So here fragments are these individual little squares that that rasterization computes and generates for us, right? So the fragments are these little parts that originate from geometric shape that was assembled from individual vertices. So these are vertices right here, right? Assembly assembles the actual triangle, right? So that's the triangle. That's the assembly of that triangle. And rasterization is generation of little parts called fragments, which eventually become pixels. Okay. So vertex processing transforms our geometry in space, so that of course we can decide how to position our objects. We can basically move them left and right and in every direction, and of course make other transformations in space as we like. This is of course programmable, because we determine how to do all these transformations using math. Clipping, we already mentioned. It's basically the idea is to assemble vertices into triangles, but also if we have our viewport, right? So this is my window where I currently display my books. So of course this window has its width and height, and so if a specific triangle does not fit perfectly into this viewport, then it has to be clipped. Basically this portion right here needs to be cut. And so normally how it happens is that because everything still has to remain a triangle, graphics hardware splits this triangle into multiple triangles like this, and so the result would be that this one will be cut off as a result of clipping, and the remaining two triangles, so this one and this one, will continue to exist in the final rasterization stages. We can also participate in this process by programming geometry shaders, but this is not something that we're going to do in our course. So rasterization is basically taking these triangles and generating arrays of fragments. So fragments are pixel candidates. So basically at the rasterization stage, there's no color assignment. Each fragment is uncolored. And final stage, fragment processing, is when we assign colors, and that's more exciting stage, because this is where the computation of lighting, the texture and material comes into place, and other types of color information. So basically this color information can be supplied by each individual vertex, right? So we can supply color information with each individual vertex and specify what color this should be. Or we can compute colors in the vertex processing stage. We can also supply colors with texture objects, and we can simply generate color in the fragment shader during the fragment processing. So there is like amazing variety of how much we can do to determine the final color of each of these fragments. And also the number of fragments really depends on the screen resolution that we're currently using, and we call fragments pixel candidates simply because multiple fragments with already assigned colors could actually be merged into a single pixel. Okay, so typically we have more fragments than actual pixels that are finally drawn on the screen. So that's why we distinguish between the fragment and the pixel. The fragment is only a pixel candidate, but the actual pixels are most often formed from multiple fragments because the resolution permits to generate more fragments than will be than the number of visible pixels. And of course, it also depends on how far or how close the actual object is, right? So if the object is far away, then of course there will be less pixels needed to draw this box, but if it comes closer, of course we get more pixels to use. And that obvious thing is that the number of fragments is also different. So just remember that fragment is a pixel candidate, but for simplicity you can think about each fragment as individual pixel.